All right, so hi everyone. I'm Danai Kutra. I'm a Maurice Wellman Assistant Professor in CSC, and it is my pleasure today to introduce Paul Bennett, who is a Partner Research Manager for the Productivity and Intelligence Group in Microsoft Research. Paul has researched many topics, including the use of, surrounding the use of machine learning in information retrieval, including deep learning for ranking and retrieval, ensemble methods, calibration, active learning, crowdsourcing, and more. His work has attracted prestigious awards at SIGIR, CHI, and other conferences. Now, during Paul's presentation, you can post your questions in the Q&A, not the chat, or you can raise your hand and then we'll unmute you to ask your question directly. So, Paul, the floor is yours. If you want to share your screen.
Great. It's giving me a message I cannot currently share. So let's try that again. All right. Hopefully these slides are up and people can see them now.
We cannot see them yet.
Just the desktop. There we go. Perfect.
All right. So thank you, Danai. And it's great to be visiting Michigan again, even if virtually. As Danai said, I encourage people to go ahead and ask questions where they are. The talk I will be giving today is just going to give a sampling of different research in this area, especially as it applies to search and recommendation. The group that I manage actually looks at a much broader set of topics. And to start off by giving you a flavor of that, what folks in the group do, it's basically a blend of artificial intelligence, HCI, IR, and software engineering. The set of researchers and engineers that we have look at these particular topics across the board. Our focus areas tend to be in 4 key areas: robust AI, hybrid work, which you can think of as the emerging area of what does it mean for people to blend remote work and work in co-located work, as is typical, and in particular, how does it affect the information systems that we need, the interactions, or team development and software engineering, how do people interact together. Developer productivity, which looks at how developers interact and what the next generation of developers look like in terms of their representativeness of the populations they serve, and universal search and recommendation. So with that, let me jump into what the roadmap of the talk looks like. I'm going to look at specifically in the space of search and recommendation, 3 key areas. How do we actually customize search or recommendation to key domains, given we have very little labeled data? As many of you know, few-shot and zero-shot learning is increasingly important. But when you go into domains, often you still find that there's a lot of domain behavior that is important to capture. And then robust AI and transparent AI. I'll give links throughout to the citations of papers. I should say that a lot of the work that I'll talk about is work from the folks in my group. I'm not necessarily involved with all of it, and I'm happy to connect you with folks to follow up, and for those looking for internships to talk about the different opportunities that are in the group more generally. So with that, let me jump into the first question and say, how can you bootstrap something like conversation from existing interaction data, starting in a domain like search? So you have a traditional search engine, and then you say, look, I want something that behaves more conversationally. I know that people are issuing queries, but I think where we're going is that people want to actually interact like conversation, say questions and statements. How do we go from one towards the other? And in particular, you may have very little labeled data. You don't know what this looks like. How can you actually match this gap? So what I want to do is briefly review work that we've done to that, and we published in WebConf earlier this year. So let's assume that right now someone searches for something like Nissan GTR. And how we'll rephrase the conversational question is, how do we lead a conversation like somewhere a person would? So you notice that when you say something to a person, they not only answer your question, they usually provide a lead to continue the conversation. And that lead is an indication of where they think it is interesting to go. So let's make this more real. If you were to issue this query on a search engine, you might see suggestions like this. And these are suggestions of other questions that people ask. Notice they are in natural language form. They've been matched in some way. Now let's look at this and ask ourselves, are these actually good suggestions? So imagine that you actually typed this query, Nissan GTR. Do you think that first suggestion, what is Nissan GTR, would be good? More than likely, if you knew to type this, it's a fairly rare query in terms of an acronym being used there. You already know. Or how to buy used Nissan GTR in Pittsburgh. In this case, this seems a little very specific unless you happen to be sitting in Pittsburgh. The next couple looks like it's a weird pivot off of this. How is this related to that? So when we look at these, we can label these in various ways. The first one is kind of, you already probably know this. The next one's too specific. Though the next one about Nissan, if you're asking this question, you already know. And the final one just really misses overall. Now, if you think of what conversation looks like to people, let's assume the search engine answered this question. It came back with an answer right there and says, here's something about Nissan GTR. The way that people would lead a conversation is they'd say, okay, I've answered that. What do I think you're going to actually want to know next, given that I answered that? And how can I indicate that to you to help shape the conversation? So what that might look like is something like this. So what are the pros and cons of Nissan GTR? Is it the ultimate street car? All of these questions imply that you not only had something about your question answered, which might be the price, where you can buy it, the specifications, but what's the follow-up? How do we continue this? So again, returning to our question, the question is, how do we actually start identifying this? How do we know what the shape of a conversation looks like? Where do we go from just this is an idea to actually data to learn from? So the idea we had here was saying, look, can't we just imitate human behavior? Which is to say, let's assume that we already had this search engine working. We could just observe conversations. And from those observed conversations, we could learn to actually lead a conversation just like people do. Of course, this is a chicken and egg problem. If we had those things, we wouldn't need to build this and vice versa. So how will we actually get through it here? So what we did was we looked at search sessions. And search sessions with typical queries might look like this. Somebody issues one query, they issue another one, they issue another one, and this kind of goes on. Now, search sessions often have a little bit of structure in that they're related in people's minds. And in fact, if you looked at this carefully, you'd notice that this set of blue queries actually has a tie. It kind of looks like a conversation in between somebody flitting off and doing other things where they were going off and checking Facebook or going to CNN. They actually had something that looked very much like a conversation where they're doing exploration about the concept remodeling ideas. And after they find one answer, they're going to the next. And this is providing a sense of structure to what this conversation might look like. So this is a behavior that actually exists in search logs. So that raises the question, what if we could programmatically identify these type of conversations? Then can we actually learn to imitate behavior in this way? And this is what we went after. Now, what we compared it to were a set of other ways of doing typical sequence to sequence ranking or generation. I won't talk much about the generation. More ranking is what we did in this case to rank suggestions. So in this case, you can take a learned representation model like BERT and customize it to the task. You could also apply other models like MTDNN or T5. So typically the setup here is that you have some context like the query, and then you might have the suggestion that you are considering, like the particular question. PA stands for people also ask, the screen that I sent you in the front, showed you in the front. And then based on that, you might want to predict, will the user click or not, right? You could also predict other things like collect relevance judgments or look at things in aggregate, because any particular click may not provide information, but the aggregate, in other words, overall high or low CR, click-through rates, CTR might tell you. Now, when you actually look at these things, it turns out that these often are not conversation leading. So things that people click on might simply be clickbait. They raise curiosity. They don't really lead anywhere sometimes. Relevance is good in that it tells you if something's related, but it doesn't really tell you if it's useful if you already had this question answered, like how do you lead that conversation? High and low CTR doesn't get you there alone either, and you can look at all these things in isolation. They all provide some information, but they don't capture it. So essentially, taking this kind of idea from identifying these sessions, what you do then can take is these queries as context when you input into the encoder, the potential next query, and now you say, can we learn to recommend this so that such that the user's next behavior, as we saw, was the next is a highly ranked suggestion. So how do we actually go about programmatically doing this? So we said, can we actually identify this in this way from this session? So here you have, again, another example session. And when we look at this, we see that there's a particular relationship here. In particular, there's this exploration about the flu here that someone has done. And so in order to actually compute relatedness here, all we really need to know is, are these things semantically related? And if they're not semantically related, drop them. And from the rest that are semantically related, is the tie strong enough that we think it looks like a conversation? So is there a substantial amount of it? Notice that we don't need to be accurate for every session. We can just ignore a session if we're not sure. The reason is because we have huge amounts of data and we just need to filter for things that look very much like a session and ignore the rest. So in other words, high precision is okay in creating our weak supervision set, and low recall is fine. And so in order to get to this point, what we did was we implied an embedding model, which I won't talk about, but is from this paper, Generic Intent Representation and Web Search. The key part of that embedded model is that it not only computes a text relationship, it computes a relationship in the search relevance space. That paper goes on to show that the similarity in that space can be related to different types of speech acts, like specifying or exploring a topic, as well as even having the same intent. A nice tie to University of Michigan. This is actually an extension into the deep learning space of earlier work that I co-authored with a University of Michigan professor now, Kevin Collins Thompson. So for those of you who know the work on intrinsic diversity, this actually updates this to be a deep learned form that uses learned representations to compute this. So this gives us our set of sessions that look very conversation-like. And now we actually just return to this setting and we say, look, now we can actually predict, we can take these sessions as input and learn from them. So then to apply this in experiments, what we did was we wanted to control for the total amount of training data, because if that's varied, it could be that the difference in model performance is due just to the different amount of training data. So the things that we compared had, Bert learned just on clicks from the current interaction. That's the first one. The second one we called clean sessions, which is to say we actually tried to do some filtering for things and threw in some other sessions that we cleaned up a little bit. Then we looked at conversational sessions where we threw in this conversational identification. And the final thing was we focused on the conversational sessions, but also did it as multitask learning, where we incorporated signals from this different relevance and click-through rates that I mentioned earlier. So then to evaluate this, the question is how to evaluate it? Well, typically in search, the first thing you do is look at search relevance. Quite interestingly, when you look at search relevance, and you can look at it according to a number of different metrics, I won't go into detail of what these mean, it looks pretty flat when you compare all of these things. Random performance is clearly worse, but all of the other models are flat in terms that they look equally the same. So what we did was we refined this notion of what is usefulness? What does it mean to actually add information to the conversation? So that's something we want not only the suggestion to be relevant, but to be useful. And given these additional metrics, what we actually found was that this actually differentiated the behavior. And I won't go into the details, but once you put it into production, which this has gone into production, you actually see that user behavior agrees with this usefulness metric as being a distinguisher on top. In other words, if all we would have looked at was relevance in choosing what to put online, we would have never known that we were missing out on a big opportunity. We can also look at the breakdown of what happened between these models just qualitatively. And I won't go in detail in breaking this up. The key thing between what was in production at the time versus adding these deep suggestions that were learned from imitating human behavior was that the number of suggestions that were useful in the sense that they added information on top of just an answer to the current query or rephrasing the current query massively increased. So this is a case from imitating human behavior, we were able to actually start to lead a conversation, even though we didn't have conversation to start with. So the lesson I might take more generally out of it is that there is emergent behavior sometimes from multiple interactions, Being able to identify that emergent behavior over a whole session allows you to identify and imitate human behavior in more complex ways. So next, I'm going to step to the question of what happens without massive search logs, but let me pause there for a second and actually see if there are any questions on that section. And Denai, you can let me know if there are no questions.
There are no questions yet.
All right. Wait one more second to see if there are any.
Maybe I can ask something.
Yep.
How do you define usefulness?
So in detail, those are defined in detail in the paper, but a couple of things that actually came up as key. One was, still, is it relevant to the current query? But if you assume that the current query was answered, and we can provide people an indication of what the answer is by giving them other search results or examples. Do you expect people would want to know this afterwards? And one of the other conditions was, given the answer, so you can see the answer plus the query, do you think someone would have already known the answer to this question beforehand, in which case we consider that a prequel? It's not useful, right? So to put this in a more conversational space that humans do, if I said to you, I'm really thinking about right now, what are alternatives to masked language models? You would never respond to me and say, oh, that's interesting. Would you like to know about deep learning, right? If I said the first one, I know the second one, right? And how do you encode that type of knowledge? And so the ordering gives you some, but also judges can provide this type of information. People are very aware of it and what they talk about.
Makes sense. And have you observed any systematic errors in imitating human behavior?
So not so much in what we talked about in this ranked case. There is a case of kind of precision and recall in the sense that you're still kind of in a place where you may not have good information about topics that are not fairly asked about. Like, how well do you conduct a conversation that people often don't have? Where we do talk a little bit in the paper, and it's worth looking into, is when we try to apply these to generative models, we still have a little bit of a challenge, because essentially the syntactic difference from the queries going to the generation actually provides a lot of friction in going there. So how we ended up doing it was, there are some sets of natural language queries. We can re-rank those given some of these kind of distributed representations and what we have. But straight generation, we're still finding a bit challenging. We made progress actually with that since the paper, but I would say that's still an open question of like, how do you really generate in a way, and especially to new topics, because then the problem is it looks really good for what you look at, and then somebody asks something slightly off and it generates something that just doesn't make sense in that particular area.
Yeah, great. Thank you. I think we can continue, and
Great.
We'll be asking questions on the end.
Okay. And usually, the first reaction to something like this that people have at universities is, this is great. You have massive search logs. I don't have them. I can't do research like this. And I would actually say that's great. If you want to do research on massive search logs, you should go work at a company or do an internship there. And it actually turns out that there are many problems that are of interest in the search space without massive search logs. In fact, if we actually look at different search problems, there's an interesting array of different things. So first off, search in itself is long tail. Often the most interesting part of it is the fact that it's constantly hard to generalize. And to have a working search engine, if 5 people have asked the same question, you ought to be doing pretty well at that. But because of this long tail and the constantly evolving nature of the web, it means that generalization will always be the challenge. And so how do you deal with generalization? But there are actually many other cases of search where you don't have a lot of labeled data. That might be low resource languages that are rare across the world. Enterprise search, where you're actually providing a search service in different companies. Not only might you not have much labeled data for your own company, but if you're someone like Microsoft who provides this for many different companies, we don't look at other companies' data. We don't actually even know what it looks like. It's a very different privacy challenge. And so the labeled data that we have is not even necessarily for those target domains. And so you really want to say, what are the signals that I can generalize here? And there are lots of other cases like this, extreme verticals. Personalized search is another case where I mean search over your personal information store, like email search or over your own files. And then, of course, the external academic IR community, which might not have much. So the interesting thing about this is that in some sense, the search frontier here is in these areas. And the more that you say, look, I'm studying web search at a university, but I'm going to limit the types of things I do to be applicable in these scenarios, it actually broadens your opportunity for impact and says, there are many more ways that you can go about it. So let's make this concrete now. Let's say, okay, well, I don't have much training data. That's fine. I took my deep learning course, and I've already learned that everything can be answered by a very large neural language representation, right? It encodes all language. It has all semantics there. I'm pretty certain that's the answer to everything and will tell me all search relevance. So let's consider that. Somebody issues the query Tokyo travel, and we've learned from our mass language model this case that if we have a sentence like explore blank holidays and discover the best time to visit, both Seattle and Tokyo are very likely. In fact, it turns out in this embedding, they might be very similar in space. From a search point of view, if we point you to Seattle when you want to go to Tokyo, that's actually not that relevant. And so this is one of those questions of how do you customize to the space and what are your signals for learning relevance? Now, again, given massive search logs, you can actually adapt the representation to the space. But we want to specifically constrain this and say, what happens when you don't have that? Where will signals come from? How should you do? So this alone is not enough without relevance, though it's a great building block. It turns out that there is something that looks a lot like search queries that can be used generally, and that's anchor text. So it's been shown in several different papers that the distribution of text and anchor text looks a lot like search queries. There's actually a good reason for this, and I guess I should be a little more explicit about this. It's anchor text in a link that points at a document, not anchor text coming out of a document. And so if you think about this, if I write a web page and I point to Denai's web page, I might have a little descriptor, and that descriptor might be something like, streaming graph learning expert, and I point to Denai. What does that mean? This means somebody who is not Denai, in this case me, has written a description of the information that Denai is an expert at. When people issue a search query, it's somebody who's typically not the author searching and trying to describe an information need in a way that's not the author. And so this tends to resemble each other for very good reasons. Behaviorally, it looks like that. Okay, so how do we actually use that for learning? In particular, while that is like that on average, not all anchor text is useful in how it describes things and point at that. This is for a variety of reasons. One reason, if you look at a typical web page, they might have a whole bunch of links, and a lot of these links, like pictorial and GIFs, is just too general. It doesn't actually, isn't very specific about the page it points to. And so when you learn, you want to learn, okay, which are the anchor text pages that would represent good queries, and in particular, how they're relevant to things. And so we said, could we actually extend this? And so in this case, we have a bunch of candidates where we have, you can think of them as pseudo queries, and a bunch of documents that are presumed relevant. So that's why it's called a pseudo label here. So we have a bunch of these input pairs. Here's a query, here's a document. And what we really want to do is say, if only we could filter these things and identify which were actually good labels and which were bad labels, we could only pay attention to the good and the bad labels. So ideally, we could do this. Well, you could say, well, you could just go off and collect a bunch of labels. Now we're back to the space where, but we can't get many labels. So how will we do this? So let's just assume we could. If you could do it, well, then these would now be the input to how you would train a ranker. Now, given that ranker, you could actually rank different documents, right? The ranking for a set of documents for a query now gives you a ranking you could evaluate. If you could evaluate this query, now you might be able to evaluate your search engine you just built. Well, it turns out that in building this, you might only need hundreds of queries labeled in order to make a good evaluation of that ranker. In contrast, you have millions of these kind of pseudo labels. So now from this, you have a chance to actually say, look, the paradigm will be here, collect a small number of queries that you've labeled, and then throw a whole bunch of data. And what you really want to do is learn this data selector and neural ranker together so that you automatically select queries that optimize the performance of the ranker. And what you're really benefiting from in this case is that you're learning how to select data on queries that you haven't even tested. So you can plug in any text classifier here as well as any ranker. So how do you go about doing this? You can use a variety of different meta learning algorithms. In the paper here, which was a paper again at WebConf from Chenyan Zhang and some of his collaborators in the group, they looked at just a simple policy gradient method. So here you evaluate the NDCG. This now turns into a reward. The data can look like it's selecting a variety of actions. In particular, is it good or bad? And this provides you a policy gradient. And so now this integrates essentially reinforcement learning together with weak supervision and the ranker. And then you continue to iterate until convergence. So, and you can look at the paper as well as there's a lot of the code available on GitHub. The nice thing about this now is you can choose a variety of different data selectors. I won't go into details about which one we picked, as well as different neural rankers. We tried two that we often use in the group for information retrieval. One is a BERT-based ranker, and the other one is a convolutional kernel ranker. Now, when you look at the opportunities for weak supervision here, now you can look at data sets that are available academically. So in this case, the CLUE web data set is one large data set that's often used in information retrieval. It's actually used in a lot of NLP in general now because it's used to train embedding models like BERT. So everything's public. You can identify the anchors and use it. Now notice if you also had some form of weak supervision like Bing clicks or labels from different data sets, Marco is a QA data set, you could also use those. We note that that's not the point here because you really want to answer the question, what methods could I use when I don't have all of this massive data? And then we assume we have hundreds of labels for relevance. So this we felt was a more workable assumption of what would it mean to do learning with very little data. So now you can look at this in two different cases. These are just two different rankers here. So this is using the convolutional kernel model on the left, and on the right side a BERT-based ranker. So if you just learn with basic relevance, you get 1. You can throw in Marco labels. It turns out Marco really helps out the BERT-based ranker. Doesn't help so much on the left-hand side. Then you can actually throw in these other cases, like what if you don't use anchors at all, or what if you throw in all anchors? It turns out neither of these help too much, right? All anchors just have a lot of noise. But now if you have these hundreds of labels and you start learning how to actually select the right type of weak supervision, now you actually see that you get a huge gain from using that weak supervision, and it's basically able to pick out more general patterns of what are the useful types of labels to be learning from. So you can also compare this to what happens when you do have a massive enough search log. And as expected, when you have a massive enough search log, you can learn from that more effectively. But again, the question is, how do you actually learn without those things? So, sorry, I'm seeing if I can silence my phone in the background. So let me take a step back now and think about this more general area of how do we actually learn when we have very little labeled data, and what are the lessons learned? Apologies for the speaker in the background. So the first thing is that simply embeddings that capture semantics in the target space are critical. Just starting off with a more general NLP-based embedding does not capture search relevance. And what was key here was actually having some signal of things. I didn't go into the generic intent encoder, but that's actually something that captured this search relevance intent. And we did actually release that. We were able to release the embedding model for academics, and that was available for about 12 to 18 months. We had that available for others to experiment with. And that was sort of a way for us to make search logs available to academics without publishing the search log, so as we could publish the actual semantics. The second point that I'd point out is this complex behaviors can be extracted from large scale data. In particular, looking at the session label phenomena gave us a way to go beyond just single item weak supervision heuristics. But more importantly, and I think this is an area for future work as well, closing the loop between these weak supervision heuristics and automated selection is increasingly important. Identifying what are the right weak supervision heuristics is a lot of manual work. Even when you go to settings like Snorkel that allow you some automatic programming for these cases, are not good at specifying these emergent phenomena at session level, let alone automatically selecting them. Even in the case where we've already closed that in reinfo select, that was at the single item level, not at looking at more emergent phenomena. So really an opportunity for future work. Where do I see the direction of this work going more generally? The gap between information retrieval and NLP is closing. Understanding, using and applying large neural language models are key in these spaces. They're not the only thing that matters. The domain is very specific in ways, but we've been able to make them work at scale. Actually using them more generally will be an ongoing challenge of how do you actually deal with this at the scale of massive collections and fully understanding search. Do I have an embedding that represents War and Peace that I could answer any question against? We're very far from anything that looks like that. The next thing is this increasing importance of distributed representation. So as I mentioned, and this partly related to the first bullet, not only is it important to push further how we understand and represent information, because of this, approximate nearest neighbor methods are becoming more and more important in practice. The trade-offs in efficiency, if you're a systems person, what does it mean to distribute these indices and answer questions against them? What are the sets of distance functions they support, and how does this relate to learning? These are becoming more and more common questions in practice. And then more generally, what are robust learned representations that are less dependent on the target space? Ideally, we would have one representation that actually we said, look, this is the answer. This is still a great research question. So far, we haven't seen it. But again, when you think about for people actually do learn knowledge in a way where they can readily apply it to new spaces. We'd like to hope that we could get there as well. So before I go to the next section, let me pause again and see if there are any questions.
There are no questions yet, but I guess as a reminder to the audience, please post your questions in the Q&A or raise your hand so that we can unmute you and you can ask your question directly.
Okay, great. I'll go ahead and go on there. So in the next section, I'd like to think about robust AI. And so I gave a little indication of robustness in the first part, which is we often need to take a technology and go from one domain to another. We have very little labeled data. That's a step towards robustness. But robustness comes up in many different areas. And so more generally, what are some of the challenges when we think of creating AI that is robust in a way that's similar to kind of human level robustness? When you think about machine learning, and this is work that's actually coming out at Wisdom 2021, Emre Kitcherman in the group has led this, and some of his collaborators in Ad Center, as well as interns that have interned with us. So when you think about machine learning, it's really good at doing correlations, right? It searches for patterns, but finds spurious ones. So in this case, if you train something to recognize zebras, it will start seeing zebras everywhere. And this is especially problematic when you apply it to data that comes from a different distribution. It worked really well on your data set of just animals, but then you applied it to the open world and you suddenly found things that you never conceived could be there. So this comes up in many different settings, specifically that you've taken something that was learned over the distribution you thought represented the real world, and then when the real world shifts, suddenly it no longer works as well. So let's take this in one specific setting, in particular, advertising. So in advertising, we often have this observed data, and the observed data is you have some ad with quality, and you really want to know basically how likely is someone to click on the ad, given the query, the ad, and maybe some other factors like the position. You might even know something about the other ads that you're considering. And in particular, as you're optimizing this, what you really want is the counterfactual, which is to say, what if we change things? What if we change our ad system or the layout or other factors? Would people be likely to click, and in what ways? How much would it change? And the actual probability of click that you're able to predict is really important. It directly relates to, in this case, revenue and ranking. And small changes in your ability to click can actually have very large impacts on the business side of things. So you're really thinking of this as being extremely accurate. Now, more generally, this applies to many other settings. So you can think of health and care, where you often want to know, well, what if we change things just a little bit, our treatment, the distribution of what we had available. In this case, it might be a different distribution of patients because you went from one location to another where demographics vary or where the distribution of genes varies. Suddenly, things are changing, but you still want to accurately predict risk. So within the ad work, they've actually done a lot of work to actually simulate this so that they can then ask offline this question: what if we actually change things up a bit? So here they have a whole counterfactual simulation system, and this was published at Wisdom. The system is called Genie, and it allows you to predict a lot of different things about what happens when the system changes. So what happens when you change certain ads, and ultimately at the end, what you want to do is predict click and also things like revenue and other related factors that are important. So you get these query ads and keywords that go in, and now you're going to actually perform simulation in a way exactly like what's been done online. So you run this and you actually try to simulate what's going to go on. Now, the key part of this is that you have click behavior in order to accurately do it. So you're going to learn click behavior and then try to run algorithms to learn a click model and use this. So this actually helps quite a bit, works well. It turns out it doesn't hit everything. So it's very good at predicting these outputs when certain assumptions hold. And so you try to predict these different kind of KPIs. But what happens when there are massive changes to the world? In particular, these click prediction models are not robust when there's feature shift or extreme policy changes. So extreme policy changes in this case might be different page layouts, might be something as simple as 5 ads instead of 4 because it significantly changes human interaction. This might happen because things are pushed off the first page and people have to scroll. And so you see very different behavior in some of these cases that kind of fall off a sharp cliff. You can think of it as the underlying assumption is that behavior is smooth, but certain types of changes, it's not smooth. Now, what is the actual implication here is that you want to be able to understand these massive changes, primarily because if there is a massive change and you're wrong, you can, in this case for ad prediction, lose a lot of revenue in these shifts, and that fear of even losing revenue can actually stop people from experimenting and finding better spots. And again, I'll use ad prediction as a case here, but this applies to many other settings as well. So you could say, well, look, I could just randomize everything. So why not just randomize everything and then learn everything without these causal dependencies? So this is a reasonable idea. So why isn't this actually done? So in particular, if you have a randomized experiment here, you could think of the log data has all of these dependencies with this complex causal graph on the left-hand side under A here. And for the randomized data, essentially you get rid of these spurious cases in the causal graph and you get just the causal relationships. So why don't people do this more often? Well, in the case of ads, while we do have random traffic, it's essentially expensive. You can think of each bit of randomization as essentially spending real money, right? It's having an impact on the optimal point of the system. You're really basically buying information, and so it has a cost. In other cases, you don't do randomization because it's just not ethically right. So this again comes up in cases like healthcare, where there might be a small amount of exploration and randomization that you can do, especially when you sign up and the risk is low. But in many other cases, it's just not considered ethical to flip a coin and say, depending how this coin flipped, you get a treatment as a result of it. And so you might be able to collect a small amount of random data, but not enough to fully learn this. And so instead we asked this question, what if we had a large amount of observational data that had some skew to it and a small amount of randomization data? Could we combine those in a way that was effective? And so what Emre and his co-authors did was they said, hey, let's look at the causal literature, and in particular this work by Susan Athey on random forest. And the honest random forest specifically looks at ways of bootstrapping across different random amounts with the idea of aggregating and averaging out these spurious correlations. So they said, could we go one step further now and generalize this to this case where we can use as observational data together with the random data? And so there's a really nice and simple way to think of extending this, which is to say, take your random data and now learn your different trees from your different bag samples across this random data. What does this give you? This gives you this whole forest of trees where the structure has been learned from data that is truly random, and therefore you've gotten rid of some of the causal dependencies. The problem is this isn't very close to the observational data. So there's high variance in the estimates of the probabilities, partially because of how little data there is, but also how far from the distribution it is. Now, trees give you a nice way to think about, well, what if I wanted to repopulate this with other data? I could actually update the probabilities and estimate them differently. And so in this case, what we actually said was, look, you could update the node values by incorporating the values from the observational data. So the intuition that this actually relies on is that the structure comes from the random data and captures the causal factors, but the actual probabilities come from the observational data and are closer to what you can think of as the world as it behaves like now. And so then the question is, how does this actually work in practice? Does this capture and balance these things off? In particular, whenever there are these massive changes to the world, do we see a much more accurate prediction from these types of causal transfer models? Now, the nice thing about this is that this is pretty straightforward to learn. It's not that complicated. It's also easily parallelizable at scale. You can integrate it into simulation workflows easy. You can capture feature interactions, and it's also easy to explain the results in terms of kind of typical boosted decision tree models that you would look at. So you can look at it at click prediction. You can also, compare it to other things in marketplace optimization. So what happens when you compare it to A/B test data for evaluation? You know the outcomes of what actually worked and didn't. Can you predict what happened when you ran the A/B test based on the data you had before? And so you could look for big changes or things that typically have caused problems. So, what happens if you did a change from 4 to 5 text ads? Because it changes the layout, it changes human behavior. And so you see a big change. How about if you introduce very graphical features and how that affects things? You could look at things like that. Now, when you look at the distributions of features here, these are actually orders of magnitude higher than most other cases that Genie is predicting. And this kind of tells you, again, this is one of those massive shifts. Often the biggest costs are in the anomalies, not the everyday events. So how do you dampen the variance due to those large but very rare shifts? So I'm not going to go into the details of the results here, but you can look at two basic cases: click prediction and marketplace optimization. The first one looks just at predicting the probability of click more accurately. There are various ways of looking at this. I will say these results are significant, even though they look like very small numbers, again, because you're talking about large amounts of revenue. Small differences here end up being very impactful on the business end. In the marketplace optimization, you see even larger relative gains, or rather, here lower is better, in reducing the amount of error. And this is in predicting overall aggregates, like what will the overall change be in terms of aggregated over the whole calendar year? What does this add up to in terms of reduction of error? And so here you can see a case of why this is so important when you reduce error by that much in a revenue-bearing business. So this paradigm that was talked about here is an interesting paradigm in general, which is take a large amount of observational data, and in this case, a small amount of random data, but I might generalize it and say a small amount of carefully controlled data. Why is it a small amount? Because often we're limited. Again, if you think of a lot of these different applications, you might not be able to collect a lot of data, but a small data that you've collected in a way where you've controlled for it. It's either random or it's controlled according to a known propensity model. Can you actually combine these in a way to do better? Another work that I won't go into detail, but we'll point you at, we looked at this in recommendation models for things like movie recommendations. And so here, when you just learn default models, you often learn to predict things that are popular together. So popularity gets confused with being related, as well as things that happen to be dependent because they came out at similar times. So they were sort of near popular, even if they were medium popularity, but they really just came out at the same time. And so what we actually did in this case was we said, look, we have a large amount of observational data. Can we extend this with annotated data? And this annotated data was collected in a way where we learned pairwise similarities based on user input, and those pairwise similarities were enough to enable us to estimate a propensity model, even though we didn't know how data was collected there. And this is a growing thread of work. There's actually several other papers that are going after similar types of, in groups outside of Microsoft, this kind of paradigm where you think about a small amount of carefully data and observational data. And I would say this is something that I personally see growing in importance because it comes up so often and because experimentation is not always in our control. When you can directly intervene, RL methods offer you great opportunities to learn on the fly. When your interventions are limited or you can't learn at all, you need more flexibility in how you deal with the skewed distributions of the data. So how would I summarize some of the lessons in this space? So we see this over and over again, that large changes in policy, this is not just in Ad Center, but in other cases, people add new features which cause massively different results, or suddenly there's a big shift in distribution. What's an example of a big shift in distribution? Suddenly everybody starts working from home. And all the features that you had of how people behave suddenly jump within the space of days. The best that often people have gotten in many cases are guardrails to detect these things and detect what's wrong and fall back to a fallback model. We should be able to do better in how we adapt and how we learn from those distributions to rapidly adapt to shifts. Again, I think this is a large possible body of work that we can extend these. There's also increasing work that looks at GANs and how we can use GANs to extract behaviors to this space. And so you can think of this like, how do we generate items that might not be in our data set, but are reasonable proposals, and make sure that when we're training for those are robust. And you can come at that from a point of view of just totally automated or people actually labeling the GAN. So you can think of it as people, as the model proposing, I think this is realistic, could you label for me? And this is a way to think about controlling model skew more generally. So with that, let me pause again and see if there are any questions before I go into the last section. Anything tonight?
I don't see questions. I think we can move on to the last section and then we'll have questions.
Yeah. And the last section is pretty brief. So this is work that Tobias Schnabel led, was at SIG-IR. And so the general question was, how can you add transparency and control to interactive AI? More generally, think about it when you use a system. All of us use different types of search and recommendation systems. If you have Netflix, you probably have used a recommendation system, right? And when you've used it, you can think of this interactive system that you provide feedback data and it updates. But have you ever been in the case where you thought, well, I want to click like on this, or I want to give it a rating, but I'm really not sure how the system's going to change if when I want to do that. And I'm a little afraid of what will happen. Will I still see things the same? And so in talking to people, we hear this fear more often. And what we saw this as is a more general case of people really aren't sure how their feedback is going to be used in a way that affects the utility of the system for them. And so we said, look, can we actually make it more obvious of how the system will change if they take an action, rather than just show them the result of that? And so we said, how would we do this? And if we did this, would their behavior change? Would they use it? Would they prefer it? So to study it in one isolated setting, we looked at recommendations. In this case, someone could click on like, and based on like, we could show them actually a set of updated recommendations. So then the question is, well, what would transparency look like in this space? So we considered different options. Those different options were that when someone just hovered over the like button before they clicked like, we could show them how the recommendations would change. So in other words, the system itself hasn't changed, but if you click like, this is what's going to happen. We could also just, as soon as they click and we could show them that, how it changed. So this is just more being immediate, and it allows us to compare. Maybe their behavior would just change because they're getting instant feedback and it has nothing to do with being able to preview it. There's also, two kind of baselines, which is we just never show them an update. So it's fixed. And so there are many systems where you never see an update while you're using it. Maybe it happens, but you can't tell at what pace, or it's delayed. You could also consider whether or not you highlight the changes. So on the left-hand side, you see you could highlight what's different, and the right-hand side, things just refresh, but you have to figure out for yourself how the world has changed. And one of the other interesting cases of looking at behavior here was we looked at this in two ways. In particular, we looked at this with a qualitative study where we got people into the lab and had them talk out loud as they were doing it. We also did a more large scale study where we deployed this on Amazon Turk, allowed people to just use it and looked at behavioral metrics. We gave them surveys as well, but we looked at behavioral metrics like how many things did they like, what did they click on, their hovering behavior, things like that. So more things that you would use at scale in terms of learning from people's implicit behavior as a signal of what's relevant or not. The interesting thing about us looking at both of these was that if we wouldn't have done both, we wouldn't have understood the research as well. In particular, the metrics that we looked at for quantitative behavior was skewed by our past experience rather than the new experience we were designing. When we had people think out loud, it opened our eyes to a different way. And in particular, we were looking first at just clicks on likes versus not clicks, because that's all we're used to thinking. Even though we designed it for hover, we didn't think about how we aggregated the time that somebody spent hovering together with clicks, which turns out to be a signal of relevance in this case and overall engagement. It seems very obvious given we designed this, but again, you kind of miss what you're looking for. And this is a nice case of why you might want to balance, especially for HCI people looking at both of these. I'll just give you a brief excerpt of the results. So in this case, when you look at the preview modes, whether or not you show the differences or refresh, people report this basically reduces decision anxiety. But the interesting thing was that they actually felt a greater sense of control through peaking. They were hovering to see how the system would change, and they essentially started steering the system. If they liked where the recommendations were going, they clicked like. If they didn't see much value, they didn't, and so it started changing behavior significantly in how people interacted. It is important to note that the action of hovering is kind of connected to clicking, so you'd be doing it naturally anyway and doesn't take much effort. We have other work that shows once it starts taking effort, people are less likely to do it. So a nice case of how this changes behavior. More generally, it also gives you signal for implicit learning. And so this views an interactive system not just as a model, but how human behavior is shaped to work together with the model to provide the best overall experience. So some design implications just to think about, how could you help people preview changes? Can you extend this to other settings? What happens when someone interacts with AI in a certain way? How would the system change? By giving them that indication, people start to actually anticipate and behave differently. And as we extend intelligence throughout a variety of systems, I think this idea of basically giving people a preview will become increasingly important. It's also, of course, useful to help isolate what's changed and not to put all the burden on them. So finally, to wind up, just some lessons learned again. The particular effects, which I won't reiterate, but this mixed method approach, especially for HCI, it's an interesting case of where the qualitative study alone would not have given us enough information of how people perform at scale, and the at-scale data might have left us with blind spots, and having this together really complement each other. More generally, the future, I think there's going to be a lot of opportunity for looking at how do we actually indicate to people what the impact of their actions will be, and how can they use that to steer a system rather than sort of the system assume where people want to go, but to make this a joint effort and a symbiotic system. So with that, I'll wind up and take more questions. Thank you.
All right, great. Thank you, Paul. So reminder again, post your questions in the Q&A. We have about 5 minutes for questions. So let me start with a question about the last part of your talk about transparency. And I wanted to ask if you have thought about transparency in longer chains of action. So what if I like this and then dislike that, or I like both things? Would it be possible to study these more complicated effects in decision making?
Great question. I do think it's possible. I think how you go about it will depend on the application space. And so, like, to put an example of it, imagine that you're driving. For driving, if you want to say get from point A to point B, you're going to need a series of turns and different actions, right? But you can get there by just having gradients of saying, go in this direction, turn here. Whether or not you need the full list or just turn by turn is fine will depend on the setting, right? There are many settings where you kind of want to understand those things. Where does it apply to other cases? imagine you've liked 300 things and not liked others. It becomes very hard to say, if you actually remove these likes, the system would definitely not recommend this thing to you. You can say this one, if you removed it, would definitely decrease this, right? And you can give turn by turn there, but the more complex space is harder. I think in general, it's easier to point people to a destination than to suppress all things. So yeah.
Great, thank you. So Kevin Collins-Thompson has a question. So while academic researchers may not have access to commercial research logs, we do have access to rich data sets from educational applications. You mentioned ads, healthcare as domains. What's an example of a compelling application of your work to the education domain?
Yeah, and I think Kevin, from our discussion earlier too, you came in, you missed the first part, which was about search logs and what to do without search logs. But to call out something specifically with education, there's a part there specifically in looking at things like Info Select around how people interact with very sparse and personalized data. And I would say education itself is one of these cases that's highly personalized. You have a sense of what people's current background is. They have goals that they want to move towards. How do you actually help them and tailor that? In the case of interaction data, what you have is a small amount of data of what people's past backgrounds were, right? And how they searched for new classes. Did they take them or not? What other links were available to tell you about them? You know, are there things like anchor text in those cases that could help you? So I think there are other cases that can apply to that, depending on what the particular education application is.
So Jahui G is asking, how do data scientists collaborate with user interface designers when building a recommendation system?
Great question. I mean, a lot of this will depend on the specific product as well as even within the group. So within the group I lead, there are actually people who specialize in all of these areas together in the same person. So Tobias's work that I presented at the end, he's published both at in user experience settings and more HCI settings, and in fundamental machine learning areas. Those types of intersections are pretty rare within an individual person. More generally, what we do is we actually have discussions up front. So whenever somebody gives me a telemetry log, I always try to ask questions of, what does the interface look like? What does it look like when you collected it? What are your anticipated changes? Why do these things matter? Because often what influences human behavior is the UX and not what you thought. So it's a simple case that I know is, people were looking and trying to understand why some people would choose reply when they were replying to email, and other people would choose reply all. And it turned out that those two people were on two different clients, one of which the default was reply all, and one of which the default was reply. So it had nothing to do fundamentally with human behavior, but with how the UX was designed. And this comes up in a lot of different cases where small changes can actually cause large changes. And these actually really affect machine learning models. So how do you start incorporating and conditioning on this? That's a more complex problem.
Great, thank you. I have another question about the embeddings that you mentioned around the middle of your talk. So you said that you made available some semantics embeddings, and I wanted to ask about your thoughts on potential privacy concerns with sharing embeddings, given that there are works that are looking at reconstructing the original data from embeddings.
Yeah, so specifically for the gen encoder embeddings, there was a lot of filtering done to make sure that things were aggregated at some level so that there was nothing too particularly sensitive in terms of the types of the queries. Because the size of massive search logs that we have, we can aggregate over a long enough period of time to do that. What does that mean is, yeah, we don't have embeddings for every tail query in terms of if we learned it over the full data, you would get a slightly different result, but it still is a lot of value compared to what is there in academia. You're right that there is a more general concern of like, how do you verify what information is being leaked in an embedding? How do you protect against it? Is it simple enough to just basically add, things like differential privacy gradient updates to your model? Like, how do you verify that?
Great, thank you. There is another question. Andrea Nicole Valenzuela says, maybe I missed this in the beginning, but when you look at human behavior, who are the human groups you all are looking at? For example, are there different age groups, racial groups?
Great question. So a lot of it depends on the which case we are in and what we're studying. Let me speak more generally to kind of, we have a set of responsible AI practices at Microsoft. And whenever we do new studies, we have multiple kind of ethics reviews that we go through. Like you have in academia, we have an IRB board. We also have several other boards that are for, you know, if we're deriving a new product, do we go through an ethics review first that says, should this even be an area that we go into? When we're actually doing the research, a typical IRB part where we actually have the discussion, say, who are the stakeholders? You know, are we getting a representative group? How do we go about this? And what are the conclusions we're likely to draw? Are those conclusions fair to the whole population? Or are we stating limitations about who they're about? So depending on where these things go, you try to understand them, and you try to understand them relative to the stakeholders. So for certain key populations, so let's say that I was actually developing a search system for enterprise systems. I'd like to know that this is actually going to work for a broad set of enterprises. It may be a different search system for schools. And so, you know, maybe I don't actually sample people from secondary schools in order to understand that. But if I was developing them for secondary schools, then I'd have to say, look, how do I understand the stakeholders there? How do I go about collecting feedback in a responsible way and get their input?
Great, thank you. So it's a few minutes past 5, so we should conclude at this point. Well, thank you for joining us today and for giving an excellent talk. And thank you everyone for attending the seminar.
Okay, thank you for having me. I really enjoyed it. Thanks.